Lenses. Describe how a lens forms an image. Explain what determines the type of image formed by a lens. Construct ray diagrams. Distinguish between the types of images formed by lenses. Describe some optical instruments that use lenses. Describe the main parts of the human eye. Describe the three common vision problems. Describe the types of aberrations that can occur in images. The big idea: lenses change the paths of light. A light ray bends as it enters glass and bends again as it leaves. The bending, refraction, is due to the difference between the average speed of light in glass and the average speed in air. Light passing through glass of a certain shape can form an image that appears larger, smaller, closer, or farther than the object being viewed. For example, magnifying glasses have been used for centuries and were well known to the early Greeks and medieval Arabs. Today, eyeglasses allow millions of people to read in comfort, and cameras, telescopes, and microscopes widen our view of the world. What types of images are formed by convex and concave lenses? Cut off a 1 centimeter length from the end of a drinking straw. Cover one end of the short straw segment with a piece of transparent tape. Place the taped end of the straw over a small object, such as a letter or numeral in a newspaper. Use an eyedropper or the longer piece of the straw to fill the shorter piece of the straw with water. Add water until the surface bulges outward above the top of the straw. View the object through the straw from the time the water forms a convex surface until, as the water leaks out, the surface of the water becomes concave. Analyze and conclude. Observing. Describe the appearance of the image of the object as seen through the water when the surface of the water was convex and when it was concave. Predicting. How would the image appear if the surface were flat, that is, neither convex nor concave? Making generalizations. What types of images do you think are formed by convex and concave lenses? 30.1. Converging and Diverging Lenses. A lens is a piece of transparent material such as glass that refracts light. A lens forms an image by bending rays of light that pass through it. Shapes of lenses. The shape of a lens can be understood by considering a lens to be a large number of portions of prisms, as shown in figure 30.1. When arranged in certain positions, the prisms bend incoming parallel rays so that they converge to or diverge from a single point. The arrangement shown in figure 30.1a is thicker in the middle. It converges the light. Figure 30.1. A lens may be thought of as a set of prisms. A. Incoming parallel rays converge to a single point. B. Incoming rays seem to diverge from a single point. 30.1. A lens may be thought of as a set of prisms. A. Incoming parallel rays converge to a single point. B. Incoming rays seem to diverge from a single point. The arrangement in figure 30.1b is thinner in the middle. It diverges the light. In both arrangements, the most net bending of rays occurs at the outermost prisms, for they have the greatest angle between the two refracting surfaces. No net bending occurs in the middle prisms, for its glass surfaces are parallel and rays emerge in their original direction. Real lenses are made not of prisms, of course, but of solid pieces of glass or plastic with surfaces that are usually ground to a spherical shape. Figure 30.2 shows how smooth lenses refract rays of light and form wave fronts. The lens in figure 30.2a is a converging lens. Figure 30.2, wave fronts travel more slowly in glass than in air. In the converging lens, the wave fronts are retarded more through the center of the lens and the light converges. B, in the diverging lens, the waves are retarded more at the edges and the light diverges. A converging lens, also known as a convex lens, is thicker in the middle, causing rays of light that are initially parallel, straight wave fronts, to meet at the single point called the focal point. The lens in figure 30.2b is a diverging lens. A diverging lens, also called a concave lens, is thinner in the middle, causing the rays of light to appear to originate from a single point. Key features of lenses. Figure 30.3 illustrates some important features of a lens. The principal axis of the lens is the line joining the centers of the curvature of its surface. The focal point for a converging lens is the point at which the beam of light parallel to the principal axis converges. 30.3, the key features of a converging lens include the principal axis, focal point, and focal plane. Study carefully. The focal plane is a plane perpendicular to the principal axis that passes through either focal point of a lens. For a converging lens, any incident parallel beam converges to a point on the focal plane. A lens affects light coming from the right in the same way as light coming from the left, or has the same effect on light incident from either side. Therefore, a lens has two focal points and two focal planes. When the lens of a camera is set for distant objects, the film is in the focal plane behind the lens in the camera. For a diverging lens, an incident beam of light parallel to the principal axis is not converged to a point, but is diverged so that the light appears to originate from a single point. The focal length of the lens, whether converging or diverging, is the distance between the center of the lens and its focal point. When the lens is thin, the focal lengths on either side are equal, even when the curvatures on the two sides are not. Notes. Learning about lenses is a hands-on activity. Not manipulating lenses while learning about them is like taking swimming lessons out of water. Concept check. How does a lens form an image? 30.2, image formation by a lens. With unaided vision, an object far away is seen through a relatively small angle of view, as shown in figure 30.4a. When you are closer, the same object is seen through a larger angle of view, as illustrated in figure 30.4b. This wider angle allows the perception of more detail. Magnification occurs when the use of a lens allows an image to be observed through a wider angle than would be observed without the lens, and so more detail can be seen. A magnifying glass is simply a converging lens that increases the angle of view and allows more detail to be seen. The type of image formed by a lens depends on the shape of the lens and the position of the object. Figure 30.4, with unaided vision, the size of an object appears to change depending on your distance to the object. A distant object is viewed through a narrow angle. B, when the same object is viewed from a closer distance and thus through a wider angle. more detail is seen. Image formed by converging lenses. When you use a magnifying glass, you hold it close to the object you wish to see magnified. This is because a converging lens will magnify only when the object is between the focal point and the lens, as shown in figure 30.5. The magnified image will be farther from the lens than the object and right side up, erect. If a screen were placed on the image distance, no image would appear on the screen because no light is actually directed to the image position. The rays that reach your eye, however, behave as if they came from the image position, so the image is a virtual one. Recall from Chapter 29 that a virtual image originates from a location where light does not actually reach. Figure 30.5, a converging lens can be used as a magnifying glass to produce a virtual image of a nearby object. When the object is far enough away to be beyond the focal point of the converging lens, light originating from the object and passing through the lens converges and can be focused on a screen, as illustrated in figure 30.6. An image formed by converging light is called a real image. A real image formed by a single converging lens is upside down inverted. Converging lenses are used for projecting motion pictures onto a screen. Images formed by diverging lenses. When a diverging lens is used alone, the image is always virtual, right side up, and smaller than the object, as can be seen in figure 30.7. It makes no difference how far or how near the object is. Figure 30.6. A converging lens forms a real upside down image on a more distant object. Why is the greater part of the photograph in figure 30.7 out of focus? Both Jamie and his cat and the virtual image of Jamie and his cat are objects for the lens of the camera that took this photograph. Since the objects are at different distances from the camera lens, the respective image are at different distances with respect to the film in the camera. So only one can be brought into focus. 30.7, a diverging lens always produces a virtual image. A diverging lens is often used for the viewfinder on a camera. When you look at the object to be photographed through the viewfinder, you see a right side up virtual image that approximates the same proportions as the photograph to be taken. Concept check. What determines the type of image formed by a lens? 30.3, constructing images through ray diagrams. Ray diagrams show the principal axis that can be used to determine the size and location of an image. An example of a ray diagram is shown in figure 30.8. The size and location of the object, its distance from the center of the lens, and the focal length of the lens are used to construct a ray diagram. An arrow is used to represent the object, which may be anything from a microbe viewed in a microscope to a galaxy viewed through a telescope. For simplicity, one end of the object is placed right on the principal axis. Figure 30.8. In a ray diagram, the three useful rays from the object converge on the image. The location of the image is found by extending the rays backwards to the point where they converge. The virtual image that is formed is magnified and right side up. You have three distinct rays. The first ray goes from the tip of the object through the top of the lens, through the focal point between the lens and the image to the tip of the image. The second ray goes diagonally from the tip of the object right through the center of the lens to the tip of the image. And the third ray goes from the tip of the object through the focal point, which is between the object and the lens, through the bottom of the lens, straight to the tip of the image. Those three rays are going to be very important when resolving the various problems of image projection using lenses. The three principal rays. To locate the position of the image, you only have to know the paths of two rays from a point to the object, represented by the vertical arrow. Any point except for the point on the principal axis will work, but it is customary to choose a point at the tip of the arrow. The path of one refracted ray is known from the definition of the focal point. A ray parallel to the principal axis will be refracted by the lens to the focal point as shown in figure 30.8. Another path is known through the center of the lens where the faces are parallel to each other. A ray of light will pass through the center with no appreciable change in direction. Therefore, a ray from the tip of the arrowhead proceeds in a straight line through the center of the lens. A third path is known. A ray of light that passes through the focal point in front of the lens emerges from the lens and proceeds parallel to the principal axis. All three paths are shown in figure 30.8, which is a typical ray diagram. The image is located where the three rays intersect. Any two of these three rays is sufficient to locate the relative size and location of the image. The ray diagram for a converging lens used as a magnifying glass is shown in figure 30.9. In this case, where the distance from the lens to the object is less than the focal length, the rays diverge as they leave the lens. The rays of light appear to come from a point in front of the lens, same side of the lens as the object. 30.9. The ray diagram for a magnifying glass shows that when the object is less than one focal length from the lens, the image is virtual, right side up, and magnified. The three rays useful for construction of a ray diagram are summarized. 1. A ray parallel to the principal axis that passes through the focal point on the opposite side. 2. A ray passing through the center of the lens that is undeflected. 3. A ray through the focal point in front of the lens that emerges parallel to the principal axis after refraction by the lens. Notes. We use these particular rays only because their pass through the lens are easy to predict. You should know that all light passing through a lens contributes to image formation. Ray diagrams for converging and diverging lenses. The ray diagrams in figure 30.10 show image formation by a converging lens as an object initially at the focal point is moved away from the lens along the principal axis. Since the object is not located between the focal point and the lens, all the images that are formed are real and inverted. As illustrated in figure 30.11, the method of drawing ray diagrams applies also to diverging lenses. A ray parallel to the principal axis from the tip of the arrow will be bent by the lens as if it had come from the focal point. A ray through the center goes straight through. Notes, interestingly, when half a lens is covered, half as much light forms the image. This does not mean half the image is formed. Even a piece of broken glass can form a complete image on a screen. Try it and see. A ray heading for the focal point on the far side of the lens is bent so that it emerges parallel to the axis of the lens. On emerging from the lens, the three rays appear to come from a point on the same side of the lens as the object, which defines the position of the virtual image. The image is nearer to the lens than the object, smaller than the object, and right side up. The image formed by a diverging lens is always virtual, reduced, and right side up. Concept check. What information is used to construct a ray diagram? Figure 30.10. The ray diagrams illustrate the formation of an image when the object is at various positions in relation to a converging lens of focal length f. You can study these two situations, and what I did was I split the figure 30.10 up onto 3 slides so you can see all 5 situations on 3 slides. The next slide is going to have 2 additional situations. Study these as well very carefully. You can see the object is put in different locations, and the image that results is shown. And then this is the last situation. Clearly, this is an example of a particular situation that you may find yourself in. What might that be? Can you guess what an application of this situation may be? And 30.11, the ray diagram shows how a virtual image is formed by a diverging lens. This particular thing will be 5 separate problems, A through E, relative to describing a lens, object, and image setup. Take each one individually and try to answer it yourself before the solution appears. Good luck. Where must an object be located so that the image formed by a converging lens will be A, at infinity? The object should be A, at one focal length from the lens at the focal point. See figure 30.10. Where must an object be located so that the image formed by a converging lens will be B, as near the object as possible? The object should be B, within one focal length of the lens. See figure 30.9. Where must an object be located so that the image formed by a converging lens will be C, right side up? The object should be C, within one focal length of the lens. See figure 30.9. Where must an object be located so that the image formed by a converging lens will be D, the same size? The object should be D at 2 focal lengths from the lens. See figure 30.10. The object should be E, between 1 and 2 focal lengths from the lens. See figure 30.10. (30.4) Image formation summarized. A converging lens forms either a real or a virtual image. A diverging lens always forms a virtual image. A converging lens is a simple magnifying glass when the object is within one focal length of the lens. The image is then virtual, magnified, and right side up. When the object is beyond one focal length, a converging lens produces a real inverted image. The location of the image depends on how close the object is to the focal point. If it is close but slightly beyond the focal point, the image is far away, as with a slide protractor or movie projector. If the object is far from the focal point, the image is nearer, as with a camera. In all cases where a real image is formed, the object and the image are on opposite sides of the lens. When the object is viewed with a diverging lens, the image is virtual, reduced, and right side up. This is true for all locations of the object. In all cases where a virtual image is formed, the object and the image are on the same side of the lens. Concept check. What types of images are produced by lenses? 30.5. Some common optical instruments. The advent of eyeglasses probably occurred in Italy in the late 1200s. If anybody at the time or before viewed objects through a pair of lenses held far apart, one in front of the other, there is no record of it. For curiously enough, the telescope wasn't invented until some 300 years later. Today, lenses are used in many optical instruments. Optical instruments that use lenses include the camera, the telescope, and binoculars, and the compound microscope. Camera. A camera consists of a lens and a sensitive film, or light detecting chip, mounted in the light tight box. In many cameras, the lens is mounted so that it can be moved back and forth to adjust the distance between the lens and the film. The lens forms a real inverted image on the film or chip. Figures 30.12 shows a camera with a single, simple lens. In practice, most cameras make use of compound lenses to minimize distortions called aberrations. The amount of light that gets to the film is regulated by a shutter and a diaphragm. The shutter controls the length of time that the film is exposed to light. The diaphragm controls the opening that light passes through to reach the film. Varying the size of the opening, aperture, varies the amount of light that reaches the film at any instant. Figure 30.12. In a simple camera, the lens forms a real, inverted image on the film. The digital camera linked to technology. Rather than focusing on image onto film, the lens in a digital camera focuses light onto an array of millions of tiny light-sensitive semiconductor photocells. Each cell produces an electrical signal in proportion to the amount of light hitting it. Usually red, green, and blue filters on the different photocells make them sensitive to a particular color of light. All of the intensity and color information is relayed from the photocell array to the computer chip. Software processes the raw information to produce an image. Telescope. A simple telescope uses a lens to form a real image of a distant object. The real image is not caught on film but is projected in space to be examined by another lens used as a magnifying glass. The second lens, called the eyepiece, is positioned so that the image produced by the first lens is within one focal length of the eyepiece. The eyepiece produces an enlarged virtual image of the real image. When you look through a telescope, you are looking at an image of an image. Figure 30.13 shows the lens arrangement for an astronomical telescope. The image is inverted, and thus the image of the man on the moon would appear upside down. 3013. An astronomical telescope forms an inverted image. For simplification, the image is shown close here. It is actually located at infinity. A third lens, or a pair of reflecting prisms, is used in the terrestrial telescope, which produces an image that is right side up. A pair of these telescopes side by side, each with a pair of prisms, makes up a pair of binoculars, like those in figure 3014. Since no lens transmits 100% of the light incident upon it, astronomers prefer the brighter, inverted images of the two-lens telescope to the less bright, right-side-up images that a third lens or prisms would provide. For non-astronomical uses, such as viewing distant landscapings or sporting events, right side up images are more important to the viewer than brightness, so the additional lens or prisms are used. Figure 3014. Each side of a pair of binoculars uses a pair of prisms that flip the image right side up. Compound microscope. A compound microscope uses two converging lenses of short focal length arranged as shown in figure 3015. The first lens, called the objective lens, produces a real image of a close object. Since the image is farther from the lens than the object, it is enlarged. A second lens, the eyepiece, forms a virtual image of the first image, further enlarged. The instrument is called a compound microscope because it enlarges an already enlarged image. Figure 3015, a compound microscope uses two converging lenses. 30.6, the eye. In many respects, the human eye is similar to the camera. A diagram of the eye shown in figure 30.16. The main parts of the eye are the cornea, the iris, the lens, and the retina. Light enters through the transparent covering called the cornea. The amount of light that enters is regulated by the iris, the colored part of the eye that surrounds the pupil. The pupil is the opening in the iris through which light passes. Light passes through the pupil and lens and is focused on a layer of tissue at the back of the eye, the retina, that is extremely sensitive to light. Figure 3016. Light enters the human eye through the cornea, passes through the pupil and lens, and is formed on the retina. Different parts of the retina receive light from different directions. The retina is not of uniform sensitivity. There is a small region in the center of our field of view where vision is most distinct. This spot is called the fovea. Much greater detail can be seen at the fovea than off to the side, the blind spot. There is also a blind spot in the retina where the nerves carrying all the information leave the eye in a narrow bundle. This is the blind spot. You can demonstrate that you have a blind spot in each eye if you hold this book at arm's length. Close your left eye and look at the round dot in figure 30.17 with only your right eye. You can see both the round dot and the X at this distance. Figure 30.17. Try to find your blind spot in each eye. If you now move the book slowly towards your face with your right eye still fixed on the dot, you'll reach a position about 20 to 25 centimeters from your eye where the X disappears. To establish the blind spot in your left eye, close your right eye and similarly look at the X with your left eye so that the dot disappears. With both eyes open, you'll find no position where either the X or the dot disappears, because one eye fills in the part of the object in which the other eye is blind. Repeat the exercise of figure 3017 with small objects on various backgrounds, the camera and the eye. In both the camera and the eye, the image is upside down, and this is compensated for in both cases. You simply turn the camera film around to look at it. Your brain has learned to turn around images it receives from your retina. A principal difference between a camera and the human eye has to do with focusing. In a camera, focusing is accomplished by altering the distance between the lens and the film or chip. In the eye, most of the focusing is done by the cornea, the transparent membrane at the outside of the eye. Notes: the giant squid has the largest eyes in the world. Adjustments in focusing of a large image on the retina are made by changing the thickness and shape of the lens to regulate its focal length, as shown in figure 3018. This is called accommodation and is brought about by the actions of the cilia muscles which surround the lens. Concept check. Name the main parts of the human eye. Figure 3018. The shape of the lens changes to focus light on the retina. Photographer. Physics on the job. Photography blends art with physics. A photographer's ideas are based on artistry, but the execution relies on a savvy use of physics and, for most photographers now, computer technology. A photographer knows that a camera seldom records just what the eye sees. Our eyes can discern detail simultaneously both in dark shadows and in light that is millions of times brighter. Neither film nor digital image sensors can do this. Hence, the photographer's experiments with brightness and contrast. The photographer who has knowledge of physics, of light, and optics is better able to use available software to turn a digital image into a work of art. 30.7. Some defects in vision. If you have normal vision, your eye can accommodate to clearly see objects from infinity, the farthest point, down to 25 centimeters, the near point which normally recedes for all people with advancing age. Unfortunately, not everyone has normal vision. Three common vision problems are farsightedness, nearsightedness, and astigmatism. Farsightedness. A farsighted person has trouble focusing on nearby objects because the eyeball is too short or the cornea is too flat so that images form behind the retina. As figure 3019 illustrates, farsighted people have to hold things more than 25 centimeters away to be able to focus them. The remedy is to increase the converging effect of the eye. This is done by wearing eyeglasses or contact lenses with converging lenses. Converging lenses will converge the rays that enter the eye sufficiently to focus them on the retina instead of behind it. Nearsightedness. A nearsighted person can see nearby objects clearly, but does not see distant objects clearly because they are focused too near the lens in front of the retina. As depicted in figure 3020, the eyeball is too long or the surface of the cornea is too curved. Figure 3019, the eyeball of the farsighted eye is too short. A converging lens moves the image closer and onto the retina. Figure 3020, the eyeball of the nearsighted eye is too long. A diverging lens moves the image farther away and onto the retina. A remedy is to wear corrective lenses that diverge the rays from distant objects so that they focus on the retina instead of in front of it. Astigmatism. Astigmatism of the eye is a defect that results when the cornea is curved more in one direction than the other, somewhat like the side of a barrel. Because of the defect, the eye does not form sharp images. The remedy is cylindrical corrective lenses that have more curvature in one direction than the other. Concept check. Name and describe the three common vision problems. 30.8. Some defects of lenses. No lens gives a perfect image. The distortions in an image are called aberrations. By combining lenses in certain ways, aberrations can be minimized. For this reason, most optical instruments use compound lenses, each consisting of several simple lenses instead of a single lens. Two types of aberrations are spherical aberration and chromic aberrations. Spherical aberrations result when light passes through the edges of a lens, as in figure 3021A, and focuses at a slightly different place from light passing through the center of the lens. Figure 3021A. Spherical aberrations occurs when light passes through the edges of a lens. B. Chromic aberrations occurs because different colors of light travel at different speeds. This can be remedied by covering the edges of a lens, as with a diaphragm in a camera. Spherical aberrations is corrected in good optical instruments by a combination of lenses. Chromic aberrations is the result of the different speeds of light of various colors and hence the different refractions they undergo, as shown in figure 3021B. In a simple lens, red light and blue light bend by different amounts, as in a prism, so they do not come to focus in the same place. Achromic lenses, which combine simple lenses of different kinds of glass, correct this defect. In the eye, vision is sharpest when the pupil is smallest because light then passes through only the center of the eye's lenses where spherical and chromatic aberrations are minimal. Also, light bends the least through the center of the lens, so minimal focusing is required for a sharp image. You see better in bright light because your pupils are smaller. Methods of correcting vision. An alternative to wearing eyeglasses for correcting vision is contact lenses. A more recent option is LASIK, acronym for laser-assisted in situ keratomileusis, the procedure of reshaping the cornea using pulses from a laser. Another recent procedure is PRK, or photorefractive keratectomy. Still another is intralace, where intraocular lenses are implanted in the eye like a contact lens, a procedure of choice for extremely nearsighted or farsighted people and for those who can have laser surgery. The wearing of eyeglasses and contact lenses may soon be a thing of the past. Concept check. Name the types of aberrations that can occur in images formed by lenses. Can a pinhole improve your vision? Poke a tiny hole in a piece of paper or cardboard. Hold the pinhole in front of your eye and close to this page. Can you see the print clearly? Why is bright light needed? Think. What advice do you have for someone who wears glasses and misplaces them and can't see the small print in a telephone book? Think, why is chromatic aberrations a problem for lenses but not for mirrors? Different frequencies travel at different speeds in a transparent medium and therefore refract at different angles. This produces chromatic aberrations. Light reflection, on the other hand, has nothing to do with the frequencies of light. One color reflects the same as any other. Lenses. A lens forms an image by bending rays of light that pass through it. The type of image formed by a lens depends on the shape of the lens and the position of the object, the size and location of the object, its distance from the center of the lens, and the focal length of the lens are used to construct a ray diagram. A converging lens forms either a real or a virtual image. A diverging lens always forms a virtual image. Optical instruments that use lenses include a camera, the telescope and binoculars, and the compound microscope. The main parts of the eye are the cornea, the iris, the lens, and the retina. Three common vision problems are farsightedness, nearsightedness, and astigmatism. Two types of aberrations are spherical aberration and chromic aberration.